Welcome back, viewers, to my channel. I am Dr. DORCAS NGIGI. We are moving on with our second topic, that is thin lenses. Now, in our last lesson, we looked at how to determine the focal length of a lens by the displacement method. Okay, where we were displacing a lens from one point to another point, and then with fixing the distance from the object to the screen, that is the image distance plus the object distance, that was fixed, which we called S. And then from that experiment, we formed two images, one very large image and a small image. That is what we expect in an actual experiment, which we shall do towards the end of this topic. Okay. Now, from there, we were able to determine the focal length, and that we did several of those. We analyzed the lens formula using different experiments. That was just one of them, and we did other three. Now, today we are going to look at something different. We are going to look at what we call the power of a lens. And the power of a lens, just like we're saying, we are measuring the strength of a lens here. Okay? How, if you have two lenses, how would you tell which one is stronger than which? Okay? What do we look for to decide this lens is more powerful than this lens? Remember, these lenses are used in different places. We use them for eye lenses. Okay, we use them in microscopes, hard lenses. Then we need to know which lens we would prefer to use where. Maybe we want a more powerful microscope, or we want just a normal microscope, or we want a simple hand lens or a powerful hand lens. So we need to know how to determine the power of a lens. Okay, so we're going to look at that. So the power of a lens, and the power of a lens is a function of the focal length of that lens. The power of a lens is a function of the focal length of that lens. If a lens is very powerful, then it means it is able to refract light to a very large degree. It can refract light more. So a more powerful lens has, in terms of refraction, we can talk about it has a larger refractive index. In terms of refraction of light, remember this aspect, you're using the aspects of refraction. So as a more powerful lens has a larger refractive index, meaning it is able to bend light more than a one that is less powerful. So it's a function of the focal length. Remember, focal length is small f. Capital F is focal point or principal focus. But this focal length should be in meters. Okay? So what does that mean? It means, you see F is on the denominator side. So it means the power, P for power, and F is the focal length. Of course, in meters. Let's drop that. So is power F, and F is focal length, and therefore P and F are inversely proportional. Why am I saying that? You see, F, the focal length, is on the denominator side. What does that mean? If this value F increases, then P will decrease because it's on the lower side. If F decreases, then P should increase. Anytime you are dividing with a larger number, you get a smaller value. When you're dividing with a smaller number, you get a larger value. So the two are inversely proportional. An increase in F will bring a decrease in P, and a decrease in F will bring an increase in P. So what does that mean in terms of power? A powerful lens will have a shorter wavelength. A powerful lens will have a shorter focal length. Okay, so when the focal length is short, then is a measure of the power of a lens. So the one with a shorter focal length is more powerful than the one whose focal length is long. Now you know about the power of a lens, and you know how to choose a more powerful length from a less powerful length. Is a measure of its focal length. The shorter the focal length, then the more powerful, the stronger the lens. The longer the focal length, then the weaker or the less powerful is your lens. That is very important in terms of power. Okay. Now the other thing I want us to look at are applications of these lenses. Mostly the converging lenses. Okay, because converging lens is the one that we use mostly. So what are some of the applications? We have already mentioned but a few, but we want to look at what we call a hand lens. So number one, look at what we call a hand lens. Now, how is this? What is the principle behind a hand lens? Now, let's say we have. Let me draw the whole of it. Let's say you have chosen your hand lens. Of course, you have put it on a support. That's your hand lens. Okay. Now, your hand lens has a center. By now you understand the center is the optical center. Then you have the principal axis, which goes through the optical center. It's also perpendicular to the lens. Okay. Then of course you have F and 2F, and that is on both sides. You have F, you have 2F. Okay. So what did we say? We want to use a hand lens as a magnifying glass. A hand lens is used as a magnifying glass. We use a hand lens as a magnifying glass. And the image we form from a hand lens, one, should be upright. We don't want an inverted image. It should be upright. And it should be magnified. That's why you're talking about magnification, magnifying glass. So the image should be upright, and it should be upright, and it should be magnified. Now, for us to get that, there is only one point we can press that object. We should press that object between the principal focus and the optical center. We said anytime the object is placed between the principal focus and the optical center, then the image is upright, it is virtual, and by virtual means it forms on the same side as the object. Now let's see this. So of course the ray that is going to come parallel is the center. I want to draw this, please don't get confused. So hit that, it will be refracted through the principal focus. Okay. The other ray that is coming from the tip of the object to pass through the to the optical center, that one we know by now should pass undeviated. So we have that. Okay, this we have in our ray diagrams, image formation by ray diagrams. So if a hope you understand. If you are not very familiar, go back to that lesson and refresh yourself. So the rays that are coming out as diverging rays. The rays that are coming out as diverging rays. Now we said diverging rays are rays that look like they are coming from somewhere. If you produce them backwards, assume you put your eye there. Your eye will not see that this ray came from here and this ray came from here. It was parallel, then it was refracted. Your eye will see a straight line, so you have to produce this line backwards. Hope I'll be able to do it much better. Okay, it should be a straight line produced backwards, and this ray here should be produced also. So you see where my rays meet, they meet at that point. Okay. So where they meet somewhere here. That's where my image is. Okay, so I'm not having a ruler, but you have a rough idea. If you have a ruler, your line should be very straight, and this one should be very straight. Now remember, we said anytime imaginary rays converge, then we form a virtue image. What are the virtue rays? Now let's identify the true rays. This ray is true. Is a true ray coming from the object. My pen is starting to lose ink. So this is a true ray which is coming from the object, and after refraction it is made to pass through that point. So this is a true ray. This is a true ray. That is a true ray. A true ray coming from the object incident to the lens, and a true ray going away from the lens. Okay? Number two, the other true ray is this ray. The ray coming from the tip of the object, passing through the optical center, moving away, far away from the lens. This ray is true, this ray is true, and that ray is true. Now, which are the virtue rays? Which are the imaginary rays? There is no ray going backwards. This ray is imaginary. It is seen by the eye as an illusion, as if it is there but it is not there. So anything you produce behind the lens is just imaginary. It is virtue. So when this ray is virtue and that ray is virtue, they are not there. Okay? The eye cannot see bending of the light. The eye sees light as a straight line. And so what the eye sees is that the imaginary rays will intersect at that point, which is seen as this true ray here is seen that this true ray is coming from here, and this true ray that is coming from the object is coming from here. So where the two imaginary rays intersect, that is where we form our image. Now our image is a virtue image. That's why it is dotted. Now what are some of the characteristics of this image? We say that an image that is virtue, as you can see, it's upright. It is the same side as the object. You are looking from this side and the image is on this side. So the object and our image are on the same side. Being virtue means it is also upright. If the object is upright, the image is also upright. If the object is inverted, the image will be inverted, the same as the object. Okay? But the most important thing about the image is that it is bigger than your object. The image is bigger than your object. It is magnified. Okay? And that is the principle of a magnifying glass. That if you put the glass, the object is on that side of the glass, and you are looking from this side, you see a larger image of your object. You see a larger image of your object. We use this mostly in biology to observe small insects and small particles. So a magnifying glass is very important. And we have just looked at the power of a lens. If you want it to have a larger magnifying power, then of course you go to the one that is more powerful. So you go to the for the one that has a shorter focal length. Okay, and so you get yourself a more powerful magnifying glass. Okay, I hope that brings us to the end of this lesson. I hope you enjoyed the lesson and you have learned something, how we use a converging lens as a magnifying glass. Don't forget to like and subscribe, and I'm hoping to see you in my next video. For now, goodbye.